All right. Today we finally get to talk about neural networks, what we've been building to really over the entirety of this course. So this is very, very exciting. You guys are going to see all the concepts that you've learned come into play here. And there's a reason why we learned the initial pieces first before just diving in and jumping into this piece. So super excited. Quick caveat, I am not feeling well. So if at any point in this I happen to just stop recording or have to mute or go off cam, we'll pick it up later. So just a pre-warning there. And we'll go ahead and get started here. So neural networks. Neural networks get their name, I'm sure you know, from the way in which our human brain operates. So they're kind of oversimplified mechanics that somewhat try to map this structure that actually exists in the human brain. So this is why they are called neural networks. And it's a subset of machine learning here, defined by the structure and function of the brain. So they are not human brains. I want to just make a clear distinction here that there are quite a bit of other mechanics going on inside of a human brain. And this is the neuron that a human brain is mapped after, where we have, dendrites here that are sending information to this nucleus inside of the cell body. And there's an axon here transmitting information to these axon terminals. And so you can see how us passing a numerical information into a function that applies a series of mathematical operations and then passes that information out to perhaps another node or another neuron. It is somewhat of an oversimplified representation of that. It's kind of like an analogy to that, but they are not the same by any means. So there's quite a few differences between the ways that the human brain thinks about things and the ways that we train these mathematical observations or operations, mathematical operations to make decisions on observations. But they both consist of some interconnected nodes, which we will refer to from here on out as neurons. And a common thing that they both do is they both take data and they recognize some patterns, and then they adjust the way that they make a decision in the future based off of that. Maybe you're a baby and you touch something hot and it burns you, and then you adjust the way that you might decide to do that in the future. And these neurons do a similar thing, using all the I was going to say technology, all of the information that we've learned about so far in this course. So they make a decision, they make a prediction, and we have a way of telling them an objective function, a loss function for telling them how correct they were. And then they adjust to try to be a little more correct next time. So those are the similarities and maybe only a few of the differences. So there's a basic structure to a neural network. Excuse me while I take a drink of water, one moment. Some terminology that will be helpful for you as you try to navigate these things is the first is nodes or neurons. So in picture form, neural networks are often represented in picture form because there can be a lot of operations going on, and it gets a little complicated to represent it quite as simply as we have in the past in one mathematical formula, because there are a lot of series of formulas, chains of formulas that are being applied. And so sometimes they're represented pictorially like this to simplify things for our human brains. And these circular elements here are each a node or a neuron. And we're going to talk about what's what does that represent? What does a node represent? And then there are layers to a network. So you can see that these nodes pass information to each other in a forward direction. And so these are your input nodes. So your first layer is always referred to as your input layer because there are no particular operations within these input nodes. You are just defining this is the data and this is where I am pushing that data to. In this case, this input layer I, is fully connected with the first hidden layer H here. So, the value that exists in this input layer here is given to this neuron, to this neuron, to this neuron, and to this neuron. And same with this, it's fully connected. Every neuron in this input layer is connected to the first layer of the hidden layer. So these are hidden layers in here. You can have n hidden layers. And this is the output layer here. So this is what your model is predicting. In this case, we have two nodes that are output. And that means that this is very likely a binary classification problem. It means we are trying to, this node probably represents the probability of class 1, and this node very likely represents the probability of class 2. So the connections are each of these nodes. In this case, it's a fully connected network. Each node is connected to each other. So we're starting to get to the point where I think it's useful to ground some of these neural network concepts on an actual data set so we can start understanding these elements as it applies to a real application, a real machine learning problem. The hello world of neural networks for image processing problems is this data set called the MNIST data set, MNIST. The National Institute of Technology, I believe it was, created this data set. And what it is it's a bunch of curated handwritten numbers. So when somebody draws the letter or number 0 or the number 1 or the number 2, it looks different. My 2 probably looks a little different from your 2, which probably looks a little different from Skylar's 2. And so somebody out there collected, this organization, collected a bunch of fairly clean samples of what handwritten digits looked like. And I believe the original intent behind this was to actually train the machines that read the US Postal Service mail to recognize addresses. So you have a handwritten letter going to somebody. This could be applied to actually read that address and put it into a machine, a form a machine could understand, to say this is the actual digitalized address based on the picture I've taken of this handwritten envelope, and to route it to the proper direction, route it to the proper mail route that it's supposed to go on. So in this data set, there's over 70,000 grayscale images. And each image represents a single digit. And this digit can range from 0 to 9. And that means we have a multi-class classification problem, as you guys are familiar with, and there are 10 categories because 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. And it's split into training and testing, 60 and 10. And these images are grayscale, and they're represented by 28 by 28 pixels. And each pixel has an intensity value that can range from 0 to 255, where 0 represents a white background and 255 represents the darkest part of the foreground, maybe the really dark part of this 8. This is important because this is how we have to represent this data in order to put it into our neural network, in order to feed it to a machine learning model. We have to figure out, hey, we have an image. How do we break this down into a numerical representation that makes sense, that we can actually feed to a machine learning model? And one way you can do that is to slice it into pixels. So you slice it into some squares and figure out how do you represent each square with a number. With grayscale, we can simplify that to a range of 0 to 255. Okay, so here is a pictorial representation of how we represent these images as data. So you can see that anywhere the space is white, it's A0. And anywhere that there is a little bit of color here, but it's not very light, or it's not very dark, it's very light. And so maybe that's an 8. And this one gets a little darker here. And so we can see that that's a 38, all the way up to, 255, maybe somewhere in here. So there's some almost like shading representation. So this is how the image is actually represented in data. So this is a list of lists. So this is the first list. This is the second list. This is the third list. I apologize. My mouth is very dry. I'm a little sick. So you can see how we could actually represent this as a matrix. We can actually represent this as a matrix, and that would be a piece of data, an object of data. And each number could be a matrix that we feed into our neural network. So that is why we have put so much emphasis on matrix representation since the very, very beginning of this course, because when we look at images, it is difficult to represent those in just one row observation. When we have a house, we can say, hey, here's all the features associated with the house, and here is one row that represents the observation of that house. When we represent an image, we actually have to represent a series of rows. We cannot represent it's legible to us to represent this image in a matrix as a matrix operation. You'll see sometimes we do transform this so that and we do apply matrix operations, linear algebra operations, so that it is at times spread out so that it's one row following another, all in one vector. So I didn't want to misspeak there. However, you can see the power of working with matrices for images. All right, let's put that into the neural network. So this is going to be our input layer. And it is 784 nodes long. There are 784 neurons in our input layer. Does anybody know why there might be 784 neurons in our input layer?
Is it all the pixels?
It is all the pixels. So if we take 28 times 28, you're going to get 784. So we're actually taking each line of this, and in this case, in this architecture that we're defining in this diagram, we are lining them up side by side. So we're passing the first one here, the second one here. When we get to number 29, we're taking this 29th pixel, and then we're just passing it to the next neuron in line. So we are actually taking this image. That's why I hesitated on the previous slide. We actually are taking this image, and we are transposing that matrix so that the data is represented as one linear observation, where it's each row, you would think of them just stacked next to each other. Does that make sense so far? Okay. And the truth is, to the neural network, that may not make sense to us, to our human eyes, but it can process and handle that just fine. And so it will begin to find patterns that exist here, patterns that exist here. And so here we have our hidden layer, which we've defined as 64 units. And in this case, our output layer is 10. Does anybody know why our output layer is 10? 10 neurons long, 10 nodes. You're almost there, Skylar. I think you were muted. Not quite. Okay, I assume I know what you were going to say, which is that we have 10 classes that we're trying to predict. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10, 1 through 9 plus 0. So we have 10 classes, so we have to have 10 output layers. Or I'm sorry, 1 output layer, we have to have 10 neurons. So here is, what is a neuron? So now I think we've grounded in that a little bit. So we're going to step back up. I'm going to jump back and forth between that example and the concepts of a neural network, so we can start to ground in that as we talk. So jumping back to talk about the structure of a neural network. We keep saying neuron in this picture, and they're just little circles with lines on them. What does that mean? We should take a moment to really understand that. And the great thing is you guys have all the tools and technology you need to really understand this. When we say a neuron, and we refer to it in this picture, we're typically referring to a mathematical formula that gets applied. That is the weights times the matrix plus the bias. You can think about this as a directly similar to logistic regression. Remember where we said y equals mx plus b, but we've got our logit function that maps the values between 0 and 1 for our y equals mx plus b. That is essentially what we're doing here with our activation function. Okay, I'm going to walk through this. We're going to start at the beginning here. In the beginning, we have our input layer here. X1 would represent the value within the first pixel for one of your images. So x sub 1 is 0. X sub 2 is 0. X sub 3, and then maybe x sub 50 or something is 232. So we have x sub 1 through x sub n. In this case, we have 784 of those. So we have x sub 1 through x sub 784. And let's just do 3 for now. We have a 3 pixel image. It's a really bad image. We have x sub 1, x sub 2, and x sub 3. It's going to be easier to talk in threes. So we have a 0, a 1, and a 7. 0, 1, 7. What we're going to do is we're going to multiply each of those by a weight, whatever randomly initialized in the beginning. And so this would be x sub 1 times weight 1, x sub 2 times weight 2, x sub 3 times weight 3. So 1 times our weight, 2 times our weight, 7 times our weight. And then we're going to also add our bias, plus b. So now we have our output of our node here is our y equals beta sub naught plus beta sub 1 times x sub 1, beta sub 2 times x sub 2, beta sub 2, or sub 3 times x sub 3. When we write that in plus our bias here, our beta sub naught, if I didn't say that already, when we write that in neural networks, they simplify all that. So we've been talking about it as beta sub naught, beta sub 1, beta sub 2. I'm going to change the terminology on you one more time. We are no longer going to say beta sub naught, it's just b. And we will refer to that only as bias. So beta sub naught, bias, b, it's now b. We will no longer say beta sub 1, beta sub 2, beta sub 3. all we're going to say is W, and W will represent a list of weights. So W is no longer a singular scalar value. It is now a list that contains all of the weights associated with this neuron here. So weight 1, weight 2, weight 3. So a list of weights. And now X is a matrix of data that we're passing in. In this case, we have our X sub 1 through X sub 3 in our example. So it's maybe in this case, it's a list of three values. Okay, are you guys following so far? Great. Then what we're going to do is we're going to wrap that in an activation function. The activation function we're going to use is sigmoid. And the sigmoid activation function is the exact same function that you guys have learned in logistic regression. So 1 over, I believe it's 1 minus e, I may have it on a slide up here at some point, to the power of negative x, or depends on what the notation is. We're to the power of negative and then this formula. And that takes the output from this neuron and transforms it to a probability that ranges from 0 to 1, that little S curve from the logic function. This is what a neuron is. You can think of a neuron in terms of the sigmoid function that we've been using as the activation function, essentially a miniature logistic regression. The notation may look different. Mathematically, it is the same operation when we use the activation function as a sigmoid. Okay, let me pause here for a second. Any questions thus far? Okay. I even had this on the next slide. So the difference with logistic regression and neural networks, there are many, and I think you'll understand that as we build through this, that's why I said earlier, it's a very gross oversimplification to say it's a series of logistic regressions, but or even linear regressions. But here is, if you wanted to do logistic regression as a neural network, you technically could. You would just set up your neural network to have exactly one neuron. You would apply sigmoid as your activation function, and you essentially have your logistic classifier here. It is mathematically the same operation that you are going to create. In neural networks, we do that many times. So we don't just have one logistic function. We have 1, 2, 3, maybe 4. Let's say we have 3 in this picture. Apologize. 1, 2, 3 in this picture, where we're passing these values to each of these. So copy and paste this logistic function 3 times. Each of them would have different weights and different biases. So they're not the same functions mathematically. And then take the output of those functions and give them to another function. So this function here also uses sigmoid activation, also takes in the bias, has a bias, and it also takes in x's, and it also applies weights to those. So there's a y equals mx plus b in here as well. Excuse me. But what it's receiving as input is now no longer a house, square footage in a house, or it's no longer receiving as input, this is the pixel value for this pixel. What it's receiving as input is, this is the transformation, mathematical transformation, the output, the logic from this neuron, and passing it into this one, and then it's applying that operation and learning weights based on the inputs that it's given here to produce an additional output. So we can see how the mathematical operations that we're putting in here can get quite expansive. And I think now it's a little easier to explain why these are sometimes termed black box models, because of the number of chained computations in a row that makes it more difficult to explain than if we just had one. All right, how are we doing? Okay, how do neurons actually learn, or neural networks actually learn? We have all of this, all these complex structures. How does this neuron here learn what the weight is here to apply to this? And how does it learn what the bias is when it's past information that's been transformed? That's what we're going to talk about here. So there are three steps that neural networks, three components to neural networks learning. The first is the forward propagation move, where the data moves through the network from the input layer towards that output layer. That is the piece we were just talking about, where each neuron runs its calculation, its own y equals mx plus b transformation, and then passes that to the next set of activation functions that have been defined that it has to pass that to, until it moves through all the layers and we get the output. That's our forward pass, our forward propagation function. Now, each of these nodes in this network have something called an activation function associated with them. It is what transforms that input, it's what transforms the output of that formula, the y equals mx plus b, the weights and biases, into what's going to be fed into the next layer. We're very familiar with the sigmoid function, which outputs probabilities between 0 and 1. But there are many other activation functions, and sigmoid is not the only one. And there are multiple activation functions that can be used within your neural network. So what you use for your hidden layer here doesn't have to be the same activation function as what you use for your output layer, for example. Then, once we have kind of the architecture defined, we've done forward propagation, we're going to do backward propagation. And this is where we see what the neural network predicted. We give it the correct answer. It calculates the difference, just like we have with, say, mean squared error. You predict the price of a house. What's the gap between that, between your, predicted price and your true price? And then it goes through a process called back propagation and some optimization algorithm, which we'll talk briefly about, such as gradient descent, to update and adjust these weights. It does this over a series of steps until the stopping criteria is met or the algorithm, the outputs converge. So this is how neural networks learn. Again, this is going to be a very high level building blocks. I'm going to give you building blocks here and enough information and terminology that you guys can explore your own learning avenues here, but not get lost in the nomenclature. So we won't go, I say that because we don't have time or really the proper background to go through back propagation in detail or gradient descent. So I'll give you some high level conceptual understanding, understand why it's important, why it exists, and how it works. But it's probably worth really digging in a little more on your own time into how this algorithm actually works. You might have to have some quick refresher on calculus to understand derivatives here. I would recommend. So loss calculation, first we're going to say how incorrect were we? So for MSE, We've got our y hat value and our y value, and we're going to take the squared error here. So once we know how incorrect we were, so this is here, we've got our y hat, and we've got our cost function. In this case, we called that loss. So we've got our cost function. We know how incorrect we were. What we're going to do, essentially, is tell this first node how incorrect it was. And then it's going to take that information and it's going to tell this other node how incorrect it was. And it's going to take this information and it's going to continue to pass that backwards, that information backwards to each node. This is a bit of an oversimplification because in calculus, we can just use a chain rule. So it's really all one formula with a series of derivatives here. But this intuitively, that is what is happening, is we're taking the value and how incorrect it was, passing it to the next node, telling this node how incorrect it was, passing that information back, this one passing that information back, it taking those two pieces of feedback, assessing how incorrect it was. And then we're going to update, we're going to apply something, an optimization function like gradient descent, we'll talk about in a minute. And then based on that, we're going to update the weights. So we're going to change our weights so that we are slightly closer to where we should be. Okay, how do we do that? How do we just change the weights so that we are slightly closer? Well, there's this really, really clever thing in calculus where you can calculate the steepness of a point. So you can, it's a derivative. You can take this point and you can say, hey, how steep is this point along this route here? And we use that to understand how close we are getting to the answer. Are we going in the correct direction? So in this picture, it's very obvious that, of course, we are going in the correct direction. We want to go down to the bottom here, but maybe in something a little more sophisticated where we start to put more parameters into our model, we have a more complex plane here, and we're sitting here, it's very helpful to tell what the slope is. What is the slope of this point right here? And are we rolling downhill, or are we perhaps, this red area would be less close to the bottom here? So we can use the gradient to tell us with respect to each, we can compute this with respect to each parameter. And kind of understand what direction we need to go. Directionally, how much do we need to adjust each parameter? There is another important piece to talk about in here, just a concept for your exploration, and that is something called a learning rate. So in addition to understanding what angle we are at, if we are at the how close to the bottom of this slope we are, we also need to understand how big you want to jump. Do we want to make a little adjustment, or do we want to make a big adjustment? And learning rate, it can be, adjustable all on its own. So you can see in this picture, as they were at the top of the slope and the gradient was rather steep and they knew they probably had a long ways to go, the jumps were really big. And then as the gradient started to level out, become closer to a flat gradient here, you can see the steps got a little smaller. The learning rate decreased. So learning rate can be a static value. It can be, take this amount of a step, adjust it by this each time. Or learning rate can be a function. It can be a function itself, and it can adjust based on the gradient, based on the steepness of this gradient or other parameters. So this is some of the tools that might be helpful as you learn and explore gradient descent and backpropagation. So there's, I think I have it on the next slide, a couple of challenges that come with gradient descent. But what is gradient descent? I think I've been talking about it and didn't talk about what it was. I probably should put this slide first. But the goal in this picture, in this scenario, is to reach a global minimum. So we want to minimize our loss. In mean squared error, if we're predicting the price of a house, we want the value of the house that we predict to be as close to the true value as possible. And that means when we take y minus y hat, it's a very small value. We're off by $1 or $0. We've minimized the loss. We've minimized mean squared error. There are other functions where you want to maximize that value. You clearly want to maximize accuracy, for example. It's not a value you'd want to minimize. You would just flip this picture upside down, and then you're just moving towards the global maximum. So the algorithm is applicable either way. It just depends on what your objective function is, if you're trying to maximize it or minimize it. Typically for visual aids, you will see, so it's gradient ascent or gradient descent, but typically for visual aids, you'll see it descending, like we're trying to minimize a parameter, or I'm sorry, minimize a loss function, a cost function, because it's easier to picture. But you could also move uphill. Okay. There are some challenges with gradient descent that I think are just interesting to know about as you start to play around with this in your mind and start to wrap your head around this. And one is that we can get stuck. There's no guarantee that we're going to find something called the global minima. So in this picture over here, it looks like maybe this one's slightly deeper than this one. So we're going to say this is the global minima. But there's a lot of local minimas. There's a lot of, sorry, I need another drink of water. There's a lot of local spots that are low points here. One is here, one is here, one is here, and they're not the ultimate. They are not the guaranteed lowest spot. So this algorithm is perhaps a greedy algorithm. It's not exhaustive. It's not guaranteed to find the absolute correct answer because it can get stuck. So in this example, where these are the steps that we're taking. So this is the, in that terminology we used on the previous slide, this is our learning rate. Here, these are the steps that we're taking based on our learning rate. And so here we get stuck in our local minima. We start taking smaller and smaller steps, and based on our algorithm and how we've defined our learning rate, and our gradient will become flat here essentially and tell us, yep, we're done. But obviously it missed this spot over here. In the real world, we don't know this spot exists, by the way. We can tell based on our training data set, and that's how we make these visuals and these things. But in the real world, when you implement this into production and you're receiving your production data, you don't know what the global minima is on your production data. All we have is our training and our test data to work with, just like everything else that we do. There are also saddle points, which this isn't the best picture of it. It's easier to view in a multi-dimensional, multiple dimensions, more than 2 dimensions, I mean, is where the gradient is 0, but it's not a maxima or a minima. And it can really cause the algorithm to stall. So here, it would actually, your gradient would become 0. And you can also have vanishing and exploding gradients, becoming extremely, extremely small, or exploding gradient's coming extremely large. And this one here, it's getting stuck in a loop. So it's bouncing back and forth. What's happening is it's calculating this gradient here and then jumping over here and then calculating the gradient here. And then it realizes it should go this way and then calculating it. And so it ends up going back and forth. I may have to pause. We may have to come back to this next time. Unfortunately, I'm sorry, guys. I have to jump off. I am not feeling well. We will see you guys later. I apologize. We'll pick up here next time.
No worries. Feel better.